So in this 10th lecture today, we will talk about fluorescence microscopy. For biology, for biological research, this variant of microscopy is possibly the most important one of all microscopy techniques. So what we'll focus on in this lecture are the principles of how fluorescence occurs, and some of the key concepts we'll talk about is how light interacts with molecules so that photons from the light fields are absorbed by molecules, and photons are also emitted by the molecules in response to being excited by light fields. And so understanding how that works, at least on a superficial level, is what we will do in this lecture and what we'll develop in this lecture. We will see that dyes have strong absorption and emission properties because they have what are called multiply conjugated bonds, and so that makes it easy for photons to be absorbed and for photons to be emitted. And the physics that we need to describe the process of fluorescence is described by the Einstein coefficients that we can use to work out the rates and the probabilities with which photons are absorbed by matter and the probabilities of light being emitted. So the brightness and the strength of a fluorophore is governed by these concepts. So one of the most important aspects of fluorescence is that it is detected against a zero background, and that's the reason why fluorescence is the most sensitive detection technique there is. In fact, of all physical interrogation techniques, fluorescence is by far the most sensitive method of anything. You can easily detect single photons now with sensitive equipment, and you can also detect single molecules very simply with commercial equipment now. This is, of course, enabled through technology advances that only 10 years ago were unthinkable. We will talk about what intrinsic fluorescence is and what extrinsic fluorescence is, and how we can make fluorescence specific. That's very important. Some molecules don't absorb light by themselves. They require extrinsic fluorescent labels for us to see them with this method. And some other molecules, such as, for example, dye molecules, they will just absorb the light without any modification to them, and so can be probed directly with light. The specificity is something that's super important. We only want to target the molecules we're interested in and not the others, because otherwise we lose contrast in the method. And the lecture 12 will therefore be concentrating on how we can get this labeling done specifically, so we can look at the things we're interested in. And finally, the two concepts of the fluorescence lifetime and the quantum yield are covered in this lecture, and you will see that through these parameters you will see why fluorescence is dependent on the local environment that a molecule sits in, resides in. So interpreting the fluorescence signal correctly, we can say something about the environment of reporter molecules, and that is very, very useful in many cases. All right, so let's jump straight in, and let's just begin by developing a few of the key concepts. So let's call this section fluorescence, and we begin by looking at important spectroscopic units that you will need to remember. So the energy of a photon is given by h times nu, and that is in joule. The units of this are joules. So h is called Planck's constant, and it's a very small number. H is equal to 6.6 times 10 to the minus 34 joules second, or joules per hertz. Hertz is per second, per hertz is second, so joule second is the unit. So you see it's a tiny number because a single photon has a tiny energy. And nu is the frequency of light, and the frequency is in hertz, or in per seconds, the units. We have already seen the angular frequency is 2 pi times nu in radians per second, and radians per second, and that allows us to rewrite this equation up here as follows. But before we do that, I need to define a quantity called h bar, which is just Planck's constant divided by 2 pi. So with that, we can also write this in angular frequency units as h bar times omega. And again, the energy of a photon is in joules. And so some useful numbers to remember, and I do urge you to become familiar with them. It makes life so much easier, because the problem with this course is that we're dealing with either very, very small numbers or very, very large numbers. The frequency of light is an enormously high number, because a light field oscillates so quickly in time. And so when you make calculations, it is very hard to have a feel whether the numbers that you get in the calculation are meaningful or not. You could easily be 6 orders of magnitude out in your calculation, but your brain isn't able to reflect on whether that number is sensible or not, because we're not in daily life used to dealing with such large or small numbers. And so by having a feel what typical numbers you might encounter in these type of calculations, it is useful to actually be able, this is a useful thing to have to make sense of what you do, and to check quickly whether you are in the right order of magnitude or not. So some of those I urge you to remember. So for example, of course, you know already the speed of light, c, is 3 times 10 to the 8 meters per second. The speed of light, as we already know, is given by the wavelength times the frequency nu, and that speed is the speed in vacuum. Or in air, where the refractive index is very similar. So we should also have some kind of a reference wavelength and a reference frequency. So green light has a wavelength of around 500 nanometers, 500 times 10 to the minus 9 meters. So that's 0.5 of a micrometer. Just to recall, a human hair has a thickness of around 50 microns, so it's about 100 times smaller than that. The wavelengths of green light. So you can fit 100 wavelengths across the width of a hair. The frequency at which green light oscillates in time is 10 to the 15 hertz. So again, that's a huge number. It's an enormous number. So 10 to the 15 times per second. So that together gives you roughly this number here. These are just in the right ballpark to get you going, so you remember those. Just to note again, 1 nanometer is equal to 10 angstroms. And that is equal to 10 to the minus 9 meters. So This is useful because a hydrogen atom has the size of around an angstrom or so. So 10 to the minus 9 meters is 1 nanometer. Okay, so do check quickly, you know, whether results are right or wrong by just, you know, using these sort of ballpark figures. You know, am I in the right frequency domain, or am I a long way out with my calculation? Could this be the right energy or not by you know, but just working out what the energy might be for a certain frequency and so on. Okay. So the next thing we'll talk about is optical transitions. So in fluorescence, we deal with transitions between different electronic states in a system. And so the system we consider here is called the two-level system. And that's all you need for this course. It's a very simplified system, so essentially you say a molecule consists of a ground state and an excited state, and all the transitions when we absorb photons and emit photons happen between these two transitions. In practice, molecules are a great deal more complicated, but we will only talk about those complications on a superficial level. But for the physics that we want to capture, the two-level system is just fine, and it actually it is all we need to do useful stuff. So let's look at this. There are three types of optical transitions between electronic states. The lower state is the ground state, so that's we denote this with energy level EM. And the excited state has an energy level En. So you go from state M to N, up. And there are three types of transition. So I draw three scenarios here. So the first scenario is that the population, the molecule you're interacting with light, is in the ground state. So it's in the lower state. So this lower state is called also the ground state, the ground electronic state. And so if a photon comes along and it has just the right energy, h nu, so that the photon energy matches the difference En minus Em exactly, then the photon can be absorbed by the molecule, the photon disappears, and as a result, the electron in the molecule goes from one orbital to another orbital, from the orbital that corresponds to energy state Em to the orbital that corresponds to the excited energy state En. And so the photon vanishes. It comes in and you get this excitation. Of course, by conservation of energy, the incoming energy is turned into internal energy of the molecule. And so for all these transitions, the key point to remember is that we need to have the energy En minus Em match the photon energy exactly. So this is key, right? Otherwise the absorption cannot take place. So this is a consequence of quantum mechanics, because these energy levels are discrete, only certain transitions are allowed. You need to supply exactly the right energy to make these transitions happen. Okay, this type of transition here is called stimulated absorption. Absorption. So sorry for that. That should be an R. And the second case, imagine that the molecule in the initial state is not in the ground state, but it actually is already in the excited state En before the photon arrives. The photon comes along, and so it comes again along at the right energy. And as a result, this drives the population back down. So the excited state is relaxed. It goes down to the lower state. So what this photon's doing, it is stimulating the molecule to give up its internal energy and emit a photon corresponding to that energy. So by conservation of energy, if that internal energy is converted into light, we get two photons coming out. The incoming one and the other one that corresponds to that internal energy that the molecule had prior to de-excitation. So you get 2 photons coming out. And in fact, this process is called stimulated emission. And so if I just continue down here for this column here, for this case, this stimulated emission is what makes a laser. And the light that comes out is coherent. So because you can think of this process, the light field comes in, I've got this excited molecule, the molecule is now, it feels the field that comes in, and the photon that comes out will come out exactly in phase with the light that came in. So the 2 photons are coherent. They have the same direction, the same phase relationship. So that is coherent light, and that's what makes the laser possible. So you prepare your molecules to be predominantly in an excited state, and then you de-excite them all in phase, and then you get this light that is very directional and propagates in the form of a beam. The final process is just happening by itself, without any requirement for an external light field or a photon coming in, and this is called spontaneous emission. So here I just draw an arrow, and just to give you a hint that this process is random and spontaneous, I draw this photon coming out at an arbitrary angle like this. You do not know which angle it will come out at and which phase the field will have, the phase of the photon coming out. So this is incoherent, and the emission is called spontaneous emission. And this is what gives rise to the fluorescence signal. So what you do is you first start usually by stimulating a molecule so it goes into the upper state, so a photon is annihilated, and then you wait, and after a certain time the molecule will just relax by itself, emit a photon, and that photon is the fluorescence emission that we want to detect. And this is incoherent. You do not know anything about the phase, so of the individual photons emitted, and the process is stochastic, so it goes into all directions. Right, so let's write down the rates at which these processes occur. So if we begin by looking at stimulated absorption, the rate at which this process here takes place is given by omega mn is b times mn u of nu. And now bmn is the Einstein coefficient for stimulated absorption, and u of nu is the spectral radiation density, and it has units of joules per cubic meter per hertz, or and per hertz is the same units as seconds. So what this means is, you know, it essentially tells you if the light field that consists of many photons shining onto the sample for excitation will have an energy in a unit volume. So if you have a volume of molecules, they're all in the ground state, and you flood them with light, and the energy density is u of nu, joules per cubic meter, per hertz, per spectral frequency interval, then the rate at which a molecule will be excited up per second is given by this Einstein coefficient for stimulated absorption, Bmn times u of nu. So that's for a single molecule, the rate at which this will happen. You know, the higher B, the more likely, the more quickly the molecule will fly up to the top, right? And of course, the higher the energy in the light field, the more quickly this will go up, which makes sense. And when we deal with lasers, so typically this will be a light field that's incoherent. So this spectral radiation density, I'm feeling quite hot around here because there are these two illumination sources here coming onto me. So I feel that there's an energy of so many joules per cubic meter per frequency interval, right? So of course the frequency spectrum of this is broad, but it's that energy field I see. But this light is non-directional, it's everywhere. But if you take a laser beam, such as what you've seen in the demonstration recently, or let's take this laser here, just to illustrate this. So if you take a laser like this, a laser that doesn't work, let me just see. No, this laser isn't doing what I wanted to do, unfortunately, so I can't show you this, but never mind. You know, you've seen the laser last time, the green spot that I used to demonstrate the slit experiment. It's very directional, right? So there, it's when you deal with laser light, it is better to deal with I nu, which is given by the speed of light c times u nu. And if you work out the units, so this is called the spectral irradiance, and obviously it's related to the spectral radiation density u of nu by just a multiplication with the speed of light, just a constant. But the units of this are they are watts per square meter per hertz. So you can see this is essentially a power flux. It's the power that goes through per unit area. So if you have a certain cross section of the beam, so it gives you the power flux through that area in per unit frequency interval, and that's very useful. So you can think of this as a power flux. So it's often easy to calculate. You just say, okay, so many photons come through that area. I can immediately work out what the power flux is. And then by multiplying or dividing by C, I get either the spectral radiation density or I get just a flux, whatever you require for the calculation. So you can, of course, then recast this equation in terms of the irradiance rather than the spectral radiation density. Okay, so the next thing is then to work out. So if I have a single molecule, this is the rate at which it will absorb. But of course, if I have an ensemble of n molecules, of which nm are in the lower state, then the total rate of transitions will be given by the number of molecules. So total number of transitions will be given by Wmn, so that's big Mn, so that's to denote a rate, is the number of molecules in this state here, Nm, so that's the number of molecules residing in energy state Em, times the Einstein coefficient for absorption, times the spectral radiation density, and that's the number of transitions per second. Okay, now we can go to the second process. Let's go to stimulated emission. So if I do that next, so stimulated emission. So here we have an equation that's similar. Note that just these subscripts are swapped around. So rather than going from m to n, the lower to the upper state, we're now going from the upper to the lower state, from n to m. And so that is given by the number of molecules in the excited state times the Einstein coefficient for stimulated emission. So that's the one that goes from n to m rather than from m to n. So from lower to upper, it goes from upper to lower. And again times u of nu, and that's again in terms of units per hertz. So BNM for most dyes is very close to what BMN are. This is not hard to, although I can't prove this to you here, I'm not going to prove it to you here. One can kind of understand if it's easy to excite a molecule up, it might be easy to stimulate the molecule down. So they are often very similar, these two coefficients. But BNM is the Einstein coefficient for stimulated emission. And so if you want to make a laser, all you need to do is you need to make sure that you have plenty more molecules in the upper state than you have in the lower state, so that this process, the stimulated emission process, dominates over the absorption process and over the spontaneous emission process. So you need both a high radiation density coming in, and you need to have a and a good population in the upper state. All right. So finally, the one that is giving rise to the fluorescence signal, which is this one here. So for spontaneous emission, we have an equation that looks like this. So here, the rate at which the population comes down is again the number of molecules in the upper state, and just multiplied by this coefficient ANM, and again that's per second, and here ANM is not surprisingly the Einstein coefficient for spontaneous emission. And so if this is the rate at which this occurs, so you could think about, let's suppose I have a population of excited molecules in state En. So I have NN molecules in this upper state here, and then I just wait, and then so you can see the rate at which these decay will depend on the Einstein coefficient. So you can sort of imagine that what you'll get is some exponential decay in time, over which the population comes down. And in fact, you can define a lifetime TFL is equal to 1 over ANM. So it just depends. If the rate ANM is very hard, so that has units of per seconds as well, the Einstein coefficient. So if ANM is very large, then the population will decay very quickly, and the fluorescence will be very strong, the signal. And if it's conversely, if it's very, very small, then the lifetime will be long, and it takes a long time for the population to come down, and the fluorescence signal will be correspondingly weaker per time interval. And this is called the natural lifetime, or the natural fluorescence lifetime, as it's called, tau FL, the natural lifetime, or the natural fluorescence lifetime. So just to make this very clear, what happens, so in these processes, absorption and emission occur when electrons in a molecule are excited into different orbitals, and when they emit, they're de-excited into other orbitals, into orbitals that have lower energy. So in fact, the orbitals that we excite and de-excite, the energies that we can reach with visible light correspond to valence electrons. So that these are weakly bound outer electrons. For the inner ones, you need very high energies, simply can't touch them with visible lights. You need X-rays or other radiation to actually get at those inner electrons, which are very firmly bound. And so, but a very important mental picture that is completely common sense that I would like you to consider is that, of course, it is somehow clear that the strength with which the electrons are bound, even the valence electrons, the more strongly they are bound, the greater the energy gaps between the lower state and the excited state will be. So you need more energy to excite them. So strongly bound electrons need blue light, energetic light, to be excited. And weakly bound electrons, on the other hand, will be more towards the red end of the spectrum, right? So it's easier to excite them, the energy gaps become smaller, and therefore lower energies in the photons, corresponding to more the red part of the spectrum, will suffice to make those transitions happen. Okay, so let's now quickly go back into this concept of the fluorescence lifetime, because it's very important. So this is a molecule that's completely left on its own, right? It will just decay. In vacuum, if you have an excited molecule, it's not affected by anything around it. It will just decay at a rate that corresponds to its natural lifetime. But usually in a cell or in water or in any environment, there are collisions and there are interactions with neighboring molecules. And of course, that affects the way at which the molecule can de-excite, because it may de-excite by just a collision rather than by emitting a fluorescence photon. So let's then look at this, the fluorescence lifetime, a little bit more carefully, the fluorescence lifetime, because it is very important for a later lecture where we talk about measuring the fluorescence lifetime in microscopic equipment. So in fact, the process, if I have an excited molecule, it can come down, as we've said, by emitting a photon at a rate ANM. But if there is a collision or any other mechanism that allows it to de-excite without emitting a photon, then the population is de-excited back to the ground state without signal. There's no photon coming. This rate is therefore called the quenching rate. So you're quenching the fluorescence. It's a loss, right, essentially, in signal. So Q is a nuisance because it reduces your signal, but actually it turns out to be also very useful for other things because it gives you information. The rate at which this quenching occurs depends on lots of different processes and gives you information. I'll go into that in a minute. So Q is the quenching rate. And so we can now put that into the lifetime. So the lifetime is the natural lifetime, A1 over ANM, but now the lifetime is reduced by that extra loss mechanism. So the population can come down much more quickly if the quenching is high. So again, these are now values that are handy to remember. So typical values. Typical values for this are ANM, the Einstein coefficient is typically 10 to the 6 per second. So it's about 1 million times a second you can expect these decay processes taking place for a molecule, a typical molecule, corresponding to a natural lifetime, TFL, of about 1 microsecond. So that would be the natural lifetime. So in isolation, a molecule in isolation. Now in liquids, for example, in a cell, that lifetime will range from 1 to 10 nanoseconds. So that's 10 to the minus 9 seconds. So that's 1,000 times almost smaller, between 100 and 1,000 times smaller than what the natural lifetime is. So in other words, in a typical environment, the probability of that quenching event taking place to de-excite is about 100 to 1,000 times larger than the probability of a photon being emitted by spontaneous emission. So there's a severe reduction in signal. But the interesting point is that this Q here depends on environmental parameters. It depends on pH. It depends on ion concentration. Some ions quench really hard, so if they're present, the quenching rate may go up. It depends on temperature. The higher the temperature, perhaps the more collisions you get, the higher the rate of quenching. The solvent polarity. So, for example, if the solvent is very highly charged, then there may be more interactions with the excited molecules, and all that gives you information. So it gives you environmental information. So if you measure the lifetime and you know the physics that affects the lifetime, you can get information about the microenvironment that the molecule that emits resides in. Okay, so the next thing that I will talk about is the subject of dyes. So if you look at fluorescent objects, for example, fluorescent marker pens, even the fluorescent solutions, dyes, colors that are used to make dyes, they absorb light and emit light, and that's what you see. And so dyes have very strong absorption and emission cross-sections or probabilities, so their Einstein coefficients are large, and the reason for that is the fact that dyes usually consist of organic molecules that have multiple bond conjugation. So what you have are you have chains or rings containing lots of pi double bonds separated by single bonds like that, and so these are said to be multiply conjugated, and the electrons reside in these orbitals here. And in fact, what then happens is that these orbitals, the electrons can now hop between these orbitals here and delocalize. That this is called delocalizations, so that the electrons are not now so firmly bound to their host atom within the molecule that you have. But they can now freely move and hop around from one to the other, and as a result of them, they're much more easily to excite. The energies required are much less than before. And also, the larger you make these molecules, the more they can move. So the electrons that you excite with the photons, they're like they act like an antenna. So the larger you make the antenna, the more easily you can move the charge around, and the greater the effect that you have. And so that gives them the brightness. So this leads to this overlap, these clouds of electrons, within which these valence electrons can move, and this is called electron delocalization. And that's very important to get strong absorption and strong emission. And so what you get is this so-called antenna effect that I just mentioned. So the bigger you make these molecules, the more conjugated bonds you have, over the larger the distance over which these electrons can move relatively freely, and so they become big antennas. So they easily absorb light and emit light, and actually this leads to red shifts for the reasons I mentioned earlier. You need less energy to excite, so you need lower energy photons, and the brightness increases. And by playing with the arrangement of these bonds and the length of the molecule, you can shift them to the red, you can change their colors, you can change their brightness, and that's how you design dyes. Okay. The next thing that's very important to discuss is the so-called fluorescence redshift. And that's also called the Stokes shift, fluorescence redshift, after famous physicist Gabriel Stokes, also called the Stokes shift. Okay, and so I've mentioned, although we haven't done it, I have mentioned that that the two-level system is a great simplification, of course, of the real molecules. A large molecule, you just seen these multiply conjugated things. Of course, these molecules are not static. These molecules can vibrate, they can rotate. And so, as a result of that, we don't deal with two-level atoms, but the electronic lower state and the electronic upper state is split into a multitude of further energy levels, vibrational energy levels and rotational energy levels. And so it is more accurate to describe these molecules where the ground state to be split into loads and loads and loads of states in the ground state, and then also a manifold of upper states like this. And so, so let's call this ground. This would correspond to EM before, and excited corresponds to EN. Although I put this in apostrophes because now, of course, this is not a single energy level, it's a multitude of levels. So each one has their own set of labels, of quantum numbers, they're called. You need many more than just M and N, you need others, but that's not important here. But let's suppose I come from the ground state. I have a molecule, it's in the ground state first. We start right down there at the bottom in this lower electronic manifold, and we put a photon in that excites it exactly to this level here. So it's one of those many sub-levels that we can excite. So these here are called vibrational levels, these ones here, and rotational levels that you can't see, they're even finer. But maybe what I've drawn here may be vibrational sub-levels. And when the molecule vibrates and collides with the surroundings, then very, very quickly, in fact, in a matter of picoseconds, you get what is called vibrational relaxation. And so what this does is actually it loses a little bit of energy. It doesn't actually emit a photon here. It'll just, dissipate it into, maybe it collides with another molecule. So that one will vibrate a little bit more. This one will vibrate a little bit less as a result of it. And then suddenly in this gets dissipated into heat and so on. So it's very easy to lose that energy. And therefore you shift these down to this lowest available substate in the upper manifold. And then from there, perhaps, you also have a further energy loss. Perhaps this whole manifold comes down by what is called solvent relaxation. And the reason... So what that means is if you have a solvent molecule, a matrix of water molecules, for example, the water molecules are polar. And so if the excited state usually is polar or more polar than the ground state, so that means the water molecule sees some kind of a charge redistribution once you excite the fluorophore. And so the dipoles now feel this. And so they will realign themselves. The water molecules will realign themselves around this excited state dipole. And that reorganization of the water environment costs energy. And so that is a further loss, and that's called solvent relaxation. And as a result then, the fluorescence, so maybe from down there now, spontaneous emission comes down at a rate A n m. And it may land in this level. It could land in this one. It could land in this one. So there are lots of possibilities now. So you cannot predict which one it is. It could be any of those. So you get a broadening of the spectrum because you have this whole width of energy levels available, and you get a fluorescence red shift or Stokes shift. So the photons that come back as signal are lower in energy than the photons that you excite the molecules with. And that redshift turns out to be super useful because it means you can discriminate the signal from the excitation beam by putting a filter in that passes this color but doesn't pass this color. As a result, fluorescence is a zero background technique. You only get signal once you have excited molecules. Otherwise, the system stays dark. And that is what makes fluorescence so exquisitely sensitive. So it's related to that redshift. I mean, if there wasn't any such redshift, if the signal were exactly the excitation wavelength, then you could just pick up scattered light from the excitation source. That isn't in fact signal, but it just comes from some spurious scattering event, some impurities in the sample or surfaces that scatter light. And they contaminate then the signal. And you can very efficiently reject this in this zero background technique. So finally, I'd like to discuss the concept of extrinsic, intrinsic, as I've promised, and specific fluorescence. And the point to make here, and let me just open my my lecture notes for this. So this will be on page 88 in the notes here. So here are the notes. If you look at this, let me just make this a little bigger here. So intrinsic fluorescence are molecules that fluoresce without any external labels. So proteins, in fact, do not fluoresce except for those that contain the aromatic residues tyrosine, tryptophan, and phenylalanine. In fact, most proteins in fact do contain these in some combination, but it's in fact only those 3 amino acid residues of the 20 there are that contain aromatic conjugated rings in the side chains. And so with these residues, you can see you have conjugated rings like that, aromatic rings. They can be excited sort of in the UV, so you can excite them at around 260 to 280 nanometers, and they emit between 250 to 400 nanometers. So you can excite intrinsic protein fluorescence, but the problem is every protein will look the same. Everything that contains these residues will give you similar signatures, and therefore it's very difficult to say, well, I want to differentiate protein A from protein B. The signatures are so similar that you can't distinguish them. So this intrinsic fluorescence is often not very useful, although you can deduce interesting things from this fluorescence. Don't get me wrong on that, but for microscopy, if you really want to say, is a certain protein present, you will not be able to determine this from the intrinsic fluorescence spectra of these of the proteins. You need to be more specific than that. It's the intrinsic signal is not specific to individual protein types. So you need to label with so-called extrinsic labels, right? For some other molecules, such as DNA and lipids, in fact, you have no choice because they do have no intrinsic fluorescence whatsoever. I mean, so not in any of the spectral regions that are useful for microscopy. You can go to the hard UV and they will become absorbent and will emit a little bit, but actually that is for most purposes not very useful. And in fact, you'd require wavelengths that are damaging to cells anyway. And so you need extrinsic labels. So you take these organic molecules, conjugated things that you design, and you find some way of attaching them with high specificity. So that subject of labeling will be the subject of not the next lecture, but the one after that one. And so with that, I finish this part, and I'll see you in the next lecture. Thank you.